All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Joel Ruben Antony Moniz. He is a senior machine learning engineer at Apple. Please join me in welcoming Joel to our virtual stage.
Thanks, Patrika. Okay, welcome everyone. So in this talk, I'm going to be dealing with how voice assistants understand named entities. So here's a quick outline of this talk. This talk is mostly going to be in three parts. The first is going to deal with what exactly is named entity understanding. The second part is going to cover why understanding named entities is such a difficult problem for voice assistants. And the third part is going to talk about what a good way to go about it might be. The third part of this talk is going to summarize joint work with several other folks from CD. A few prerequisites. The first two parts of this talk actually don't have any prerequisites. I'll be going over everything from scratch. The what's a good way to go about it section is going to assume some knowledge of machine learning and deep learning concepts, like the basic architectures like BILSTMs and CRFs and CNNs, as well as loss functions. So if you're not familiar with one of the architectures that I've just mentioned, it'll be completely okay to treat them as a black box and to look them up later. So what is named entity understanding? Let's first talk about what a named entity is. So informally, a named entity is a set of words in a sentence that refers to a single concrete entity. So in natural language processing, named entities typically refer to proper nouns. So things like a person's name or a location or an organization's name. Now, for the purpose of this talk, a named entity could typically refer to something relating to music or movies or sports. So things like song titles and music artists, movie names, movie personalities like actors, directors, producers, or sports teams, sports persons, or the places where sports teams might play, things like that. Is what a named entity would represent for the scope of this talk. And coming to what exactly named entity understanding is. Now, in the context of a voice assistant, understanding a named entity would entail understanding what parts of a user's query correspond to a named entity. So you'll hear me referring to these parts as spans. So anytime you hear a span, it just means the substring within a query that actually refers to the named entity. Understanding the type of these spans and understanding the distinct entity that each of these spans represents. And I'll be explaining these with an example. So let's think about Play Shape of You by Ed Sheeran. Now, this is something that's very common in a voice assistant. A very common interaction with a voice assistant would involve asking it to play a song. So Play Shape of You by Ed Sheeran. Now, understanding the named entities in this utterance, because the voice assistant needs to realize that Shape of You is a song and Ed Sheeran is the artist who sung it. And you might have the exact same name by, or something very similar by another artist. So to understand this entire query and understanding the named entities within it, it would first entail identifying that Shape of You and Ed Sheeran are entities. Identifying that Shape of You is a song and Ed Sheeran is the artist, and then identifying that Shape of You represents like this song and Ed Sheeran is this specific artist. So here's a question I get all the time. How hard can it be? Why not use a simple rule to solve this? I mean, if you look at Play Shape of You by Ed Sheeran, right, you could think of having a simple regex-like pattern. So play star by star, and then just assigning the whatever the first star is to a song and then the second star to an artist. Sounds simple enough, right? Over the next few slides, I'll be walking you through several challenges on what exactly makes this a really hard problem. So a big challenge is natural language can be really ambiguous. So Play Shape of You by Ed Sheeran is what we had so far. Now, that works fine, but the moment you have something like Play Cake by the Ocean, Cake by the Ocean is the actual name of the song, as opposed to Cake being a song and the ocean being an artist. Of course, in the previous slide, you could think of using how it's been capitalized to distinguish between the named entities, between the songs and the artists, and like other typological features. But here's the second challenge. Voice assistants, like by definition of a voice assistant, they can't rely on textual cues. All they have to work with are the audio. So here you could, like the typographic features that I was referring to, in this case would be the capitalization. But what a voice assistant would see, or rather hear, is actually this, where you can't use anything like capitalization to determine the boundaries. The other issue is not all languages have capitalization. English, of course, does, but then there are several languages which don't have that concept, which sort of brings me to the next challenge. Voice assistants often deal with transcription errors. These transcription errors could be due to several reasons. So background noise, accented speech, homophones, things like that. So if you think about Shape of You, someone might pronounce shape in a way that's heard like sheep by the voice assistant. So that would mean Play Shape of You by Ed Sheeran. And we'd like to know that Shape of You is actually the same as Shape of You. Likewise, Hymn for the Weekend. Now, the voice assistant might decide that it's the number 4, which is pronounced almost identically to 4. So play Hymn for the Weekend. Or it might even hear Play Hymn Weekend, just because of some background noise or because there was some interruption with the audio. And in both of these cases, we want to identify that the song being asked, being spoken about is Hymn for the Weekend. The next challenge is that virtual assistants are used all over the world. So as a fairly simple example for this, what's the football score would mean two very different things in, let's say, the UK and the US, where in the UK, you'd want to probably pull up the Championship League scores, while in the US, it could refer to Super Bowl scores. They're two completely different sports, but both called football, depending on the part of the world. Sort of similarly, named entities can be very contextual. So the exact same named entity can actually refer to two very different things. So if you think about Play Moana, if the user asks this on a HomePod, then you are guaranteed that you can't really show anything. So you definitely want to play the Moana soundtrack. If they ask this on the Apple TV, chances are they're talking about the movie. So you'd want to actually direct them to the movie. And in both cases, it's just the single word Moana that refers to two very different things. Named entities are also dynamic. So the exact same queries, when asked at different points of time, can be interpreted very differently. So the example I love giving for this is Play Thank You Next. Now, before 2018, it would mean play the song Thank You after the current song. But around the end of 2018, Ariana Grande dropped Thank You Next. And all of a sudden, this completely changes the meaning, because really the user's asking the voice assistant to play the song Thank You Next. And if they wanted it to be queued up after the current song, they'd have to say Play Thank You Next, next. And I'd also like to point out the non-standard spelling of Thank You Next that was chosen to represent the song, which brings me to challenge 7. named entities are sometimes spelled in very unexpected ways. So thank you, next, good for you. A lot of artists tend to abbreviate little to Lil, like Lil Nas X. And The Weeknd has chosen to drop the E from the name. So all of these deal with very unexpected spellings. Challenge 8 is that named entities can be really hard to remember exactly sometimes. There's several different ways that or reasons why that could be the case. So one is that sometimes the official titles can be really, really long. So for this song, you typically see like play ILY or ILY or play I Love You Baby, while the actual name of the song is ILY I Love You Baby featuring Emily. Likewise, users often refer to a song by the refrain, and that might be the case. It might be the case that that's the actual name of the song in a lot of instances, but um, sometimes they are completely different. So for this song, users might often ask, play Loving You is a losing game, because that's the most catchy part of the song, and it appears several times in the lyrics. But the actual name of the song is Arcade, which appears exactly once in the entire song, really subtly. Now, challenge 9 is that named entities are referred to with aliases. So The Rock for Dwayne The Rock Johnson, or Big Ben for Ben Roethlisberger. And this is certainly not the last challenge, but it's the last one I'll be showing today. Named entities are often ambiguous. And I'd say that this is arguably the trickiest case of them all, because it's really hard to know exactly how to disambiguate these, just because either answer could be correct. So play Post Malone. Now, Post Malone is, of course, like a very famous artist, but there's also a song by the exact name Post Malone that didn't have the artist in it, but the song was just called Post Malone. And in this case, and the song's really popular too. So in this case, it's very difficult to decide what the right approach is. So having gone through all of these challenges, what's a good way to go about solving it? This third part of this presentation is going to cover some work that we recently published, noise robust named entity understanding for voice assistants. That's going to talk about exactly what one good approach to dealing with this challenge might be. And I've listed all of my collaborators here. This was joint work with a very, very large number of people within Siri. A very quick recap about the motivation. Understanding named entities is crucial for voice assistants, like I've mentioned. And you can think about it in terms of named entity recognition and entity linking, which are standard approaches in academia, and especially when dealing with text. And I'll be describing both of these in a little more detail, but they often perform poorly on spoken utterances. So this is because utterances tend to be really short, like call John or play Post Malone, for example, with very little context. Speech recognizers make mistakes. So play Bohemian Raspberry is one, or play Sheep of You might be another. And users might make mistakes, like Cristiano Nando for Cristiano Ronaldo, or technically play ILY could be considered a mistake because it's not exactly ILY I Love You Baby featuring Emily. And of course, like non-canonical forms of names are frequently used, like Shaq Score Tonight, or Big Ben Stats, for example. And the goal is to design a robust system that can recognize and correct named entities for noisy spoken natural language utterances. So the main contributions are proposing a system which combines named entity recognition and entity linking, designing a retrieval engine, and also allowing other other downstream tasks to leverage the system. And I'll be describing each of these in much more detail. coming to the core method itself, the key idea was to split our architecture up into 3 stages, with each stage feeding into the next. So we have NER, candidate retrieval, and joint linking and re-ranking. And the candidate retrieval and linking and re-ranking are together called our EL, or entity linking system. So zooming in on each of these parts, let's say the user asks Cowboys versus Giants. And really, they're asking for the score of a sports game. So the NER module, the named entity recognition module, its purpose is to identify the spans or the chunks, as well as the types associated with each of these chunks. So in this case, it identifies that Cowboys is a sports team and Giants is another sports team. And our NER module, we actually take several hypotheses from it. So you could think of another hypothesis as being Cowboys versus Giants, the whole thing being a movie, like Aliens versus Predators. Next, we have the candidate retrieval module. So it takes the spans that the NER system predicted, the chunks and the types, and does a lookup on the knowledge bases. So you can think of this as each of these being like a search query run through a search engine. So Cowboys searched for in the sports knowledge base, and Giants searched for in the sports knowledge base again. And we retrieve all of these candidates. And the final step is to use all the information that we have so far from both the steps and to re-rank the NER hypotheses where applicable, while also predicting what the actual entity each of these corresponds to in the knowledge bases. So Cowboys normalizes to Dallas Cowboys in the knowledge base, and Giants refers to the New York Giants. So the final output that we have is going to be the chunk, Cowboys and Giants, the type, both of them being sports teams, and the names, the canonical names of these entities in the utterance. So Dallas Cowboys and New York Giants. So going into a little more detail for each of these modules, our named entity recognition is a sequence tagging model. So each token is assigned a label. The model architecture is a character embedding followed by a BILS TMCRF. So a fairly standard architecture in the world of named entity recognition here. Except normally, one tends to take the top 1 alternative. In this case, we take the top 5 alternatives. That's the hypothesis I was referring to, Cowboys versus Giants possibly being a movie, for example. We also have the sequence level, that is at the entire utterance level, as well as the mention level, the sequence level being the chunk level, and the mention level being the utterance level confidence scores as features for the ranking. The entity linking system consists of 2 steps, as I spoke about, the candidate retrieval and the joint linking and the re-ranking. The candidate retrieval is for each of the NER hypotheses that we have. It just does a search on the entities, and we index not only the entities, but also their common aliases. And this search includes relation features like which artist sang a song, for example, or which player belongs to which sports team. And then we select the top C, and here C is 25 candidates based on TF-IDF score, as well as the popularity of the entity. After the candidate retrieval is done, the next step is to assign a score for each of these hypotheses. We define an entity linking hypothesis Y with k-entity predictions as a function of multiple groups of features. And I'll go into this in a little more detail, but these features include the similarity features for each mention and candidate pair, the context features from the entire utterance, and the features from the NER model and the candidate retrieval systems. Zooming in a little on the similarity features. So to get the similarity features are the similarity between what the user mentioned as well as what is visible in the knowledge base. So Giants versus New York Giants. We use a CNN model which computes the features corresponding to both of these. We learn a named embedding with a one-dimensional CNN applied over the character sequence, and the kernel parameters are shared between both of these. And finally, we just concatenate all of the features and then apply an MLP that computes the final score for this hypothesis. To train the model, we use a max margin loss shown here. So for the ith example, we denote the ground truth as y sub I hat star, and the incorrect prediction is y sub I. And the scoring function S is defined. The max margin loss basically encourages the ground truth to be at least a margin gamma higher than the score of an incorrect prediction. The margin is defined as a function of the ground truth and the incorrect prediction. And so it's sort of adaptive to the quality of the prediction. Coming to the applications where we actually use these. So we use these in two downstream tasks, the domain classifier, which is a sequence classification task, and a shallow semantic parser, which assigns both verb and semantic labels. And we featureize these NU features as one-hot vectors times the sequence level confidence score from the NER and the linking model. So to feed in information produced by the NU system, we concatenate all of the hypotheses from the NER system alone in the first case, and also from the linking model in addition in the second case. Our data was randomly sampled from 600,000 unique anonymous English transcripts that were machine transcribed. We used an 80-10-10 train dev test split, and we used three popular domains that were very named entity heavy: music, sports, and movies and TV. Coming to our results, we use the standard NER F1 metric. And we also use a top 5 F1 score. We look at the best among the top 5 hypotheses with respect to an oracle and choose that as the top 5 F1 score. For entity linking, we measure how well the entity linking module was able to re-rank NER, and also the correct re-ranked NER span type and resolution, which we call the ELF1 score. So here you can see the NER F1 top 5 is extremely high, which means that the top 5 usually contains the correct spans and types. And we also see that the entity linking re-ranked NER F1 provides substantial gains over the NER F1 top 1 in all 3 domains. And looking at our downstream applications, we see that using NER features over the baseline gives us a fairly large improvement consistently, and using NER with entity linking in turn usually improves over just the NER features. Coming to a few qualitative examples, so Play Carla Cabello was correctly linked to Camila Cabello. Likewise, Cowboys versus Giants. The relationship between Cowboys and Giants successfully helped disambiguate between the San Francisco Giants and the New York Giants. And the New York Giants was the correct choice, and it was selected in this case. It also helps re-rank hypotheses with very little context. So the EL module. So Doctor Strange, NER said Doctor Strange is actually a person, and there was movie as a hypothesis somewhere down the line. But then the entity linking successfully re-ranked, because it's a very popular movie, re-ranked Doctor Strange as a movie instead of a person. And likewise, NER said play Avengers Age of Ultra, which is pretty noisy. It said Avengers was the name of the movie, but then our entity linking model was able to re-rank Avengers Age of Ultra as the movie, while also linking it correctly to Avengers Age of Ultra. So in summary, we proposed an NEU system to jointly identify and resolve entities in the voice assistant, with the entity linking module also possibly correcting entities recognized by NER. And it was targeted towards noisy natural language utterances. And these features helped downstream as well. So that's one way to solve the problem. And yeah, here's the first is the paper that I mainly described, and the second is recent work where we propose an alternate approach. Thank you.
Wow, Joel, thank you. That was amazing. And I know this virtual audience is giving you a huge virtual round of applause. Thank you so much for sharing with us today. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.